And we are broadcasting on YouTube. We have had a couple of questions about the homework. I think it was 8D. Oh, this is question 11 right here. And then there was question 12, and question 12 was sort of a challenge problem. But I think once you see a part of it, at least it will make sense. Okay, so 8D, I believe the question is find vertical and horizontal asymptotes and then sketch the graph. And so all of these, oh, we can also find X-intercepts. Oh, I never thought of that. Okay, and sketch the graph as well. All right, so first thing, always factor things. So let's factor the top. There's a common x squared factor in the top. Good. And x plus 1 is left over. The bottom, this throws me off because the x squared is at the wrong end. So I'm going to factor out a -1 and do the trick where you don't put the 1 in just to mix everybody up. Okay, good. Now, as I look at the top and the bottom, I can see that they are the same degree. And so basically, there's going to be a horizontal asymptote at the ratio of the coefficient of these two terms. So it's going to have a horizontal asymptote of, oh, wait, no, I'm wrong. It's going to head off for infinity. Okay, good. I was wrong about that. Really wrong. Okay. Let's look for vertical asymptotes. In other words, where the bottom is 0. And so we are going to factor the bottom, negative. And two numbers that have a sum of -1 and a product of -2 are x plus 1, x minus 2. There we go. And so that one has been laid bare. There is a vertical asymptote at x equals -1 and x equals 2.
Excuse me, sir.
Yes.
You have made a critical error.
What?
You can't factor an x squared out of x.
Oh, look at that. I made the exact same mistake. Oh, okay. All right. There we go. Okay. Good. This is going to get us the right answer after all. Okay.
Hold on, but you're still.
There we go. Fixed all the way through. How'd we do? Okay. We have a vertical asymptote. One is at x equals -1 and one is at x equals +2. Looking at the degree of the top and the degree of the bottom, I can see the degree of the top is greater than the degree of the bottom. And so basically the limit of this function as x goes to plus or minus infinity is going to be plus or minus infinity. And if you look at the graph, you can actually see, because the degree of the top is 1 more than the degree of the bottom, there is an oblique asymptote. This question isn't asking you to find oblique asymptotes. It's only asking you to find vertical and horizontal asymptotes. All right. So we have 2 vertical asymptotes. The last thing we could do in order to help us sketch the graph is look for the x-intercepts. And we can find x-intercepts by looking at places where the numerator is 0. So where x squared plus 1 equals 0. X squared plus 1 is never, ever 0. And so,
yeah, maybe not in your number system.
Unless you're in the complex number system. And so there is an x-intercept when x is equal to 0. And so if we were to draw this, now I've lost the initial equation. But we have a vertical asymptote at x equals -1. We have another one at x equals 2. I happen to know we have an oblique asymptote, and it's got a slope of 1. You don't have to do the oblique asymptote, by the way. Could be plus or minus. We also have an intercept here. it's cubic over quadratic. And so I know that it's going to start low. It's going to start down here. And when x is negative, it's going to be negative. And so it's going to avoid that vertical asymptote. It's going to pass through x equals 1. And it's going to do something like this. And then it's going to, as x heads for positive infinity, it's also going to be positive. And so there's a kind of an overview. So that is 8D.
When you have these, when they're, turn on my mic. When you have it, am I good here? Okay, nothing is exploded. Okay. So when you have it when the top is, when the degree of the top is 1 greater than the bottom, you get like a linear sort of asymptote, right? If it's 2 greater than the bottom, would you get a parabolic asymptote?
And so the answer is yes. So we get this oblique asymptote, it's linear. And then you can get a parabolic asymptote if the degree of the top is 2 more than the degree of the bottom. You can get a cubic one that's like 3 more than the degree of the bottom. Yeah. Yes.
That's funky.
Yeah, very funky. Okay. We are now moving on to question 11. And so question 11 is broken up into, it's a piecewise function, and it's broken into 3 parts. And we are supposed to find horizontal and vertical asymptotes. And so we just consider these individually, and then we try and figure out if our vertical asymptotes fall in the defined domain for each of these piecewise functions. So let's look at x plus 3 over x squared minus 4x. And the limit as x goes to positive or negative infinity of this function. So I can see the degree of the bottom is greater than the degree of the top. And so it's going to head for 0. So we are going to have horizontal asymptote, which is basically the x-axis, or y equals 0. Okay, so as x gets big, this is when x is less than 0. We are going to have a horizontal asymptote. Oh, and since x is less than 0, all we really do is we head for negative infinity. We don't have to head for positive infinity. Now, let's look at for vertical asymptotes here. In other words, when the bottom is 0. And so we're going to factor the bottom. The top doesn't need any factoring. So this, provided I don't make any mistakes here, this has a vertical asymptote, and the bottom is equal to 0. So just solving x times x minus 4 equals 0. It has a vertical asymptote when x is 0. It also has a vertical asymptote when x is 4. I don't have to worry about this vertical asymptote when x is 4. And x is less than 0, and so I don't know.
You're never going to get there.
Yeah, you're never going to get there. Definitely with a vertical asymptote, run along the asymptote, even though the asymptote might not be in the domain. Do you have a second? Is this a less than or equal to?
For 11. It is a less than.
It's a less than. Okay, so it's going to look like there's a vertical asymptote, but the vertical asymptote isn't part of the equation. Okay, let's look at the area where x is between 0 and 2. So there we go. So f at x when x is between 0 and 2. The function is cos x plus 1. So it's not a rational function. It's a trig function. It's not a reciprocal trig function. There are no vertical asymptotes. So no vertical asymptotes as well. It's just a straight trig function that's been shifted up one. And so there are no horizontal asymptotes. So this is a periodic function throughout its domain. It goes up and down, never reaches that, never reaches a horizontal asymptote. Okay, let's go for the place where f at x is greater than 2. Okay, so we have a lot of stuff going on here. So f at x is equal to x squared minus 1 over x squared minus 7x plus 10. And so it's equal to x minus 1 over x plus 1, x minus 2, x minus 5. And so I can actually see I'm going to have a couple of vertical asymptotes looking here. The degree of the top is equal to the degree of the bottom. And so the horizontal asymptote is actually going to be equal to 1. So if I wanted to do this formally, x squared over, I take the limit as x goes to positive infinity. I don't have to worry about negative infinity. X squared minus 1 over x squared minus 7x plus 10, which is the same as x squared over x squared minus 1 over x squared. So using that little trick we looked at yesterday, and of course I forgot to put my limit in here. And so these both go to 1 over 1 when I put in my limit. Everything else is 0. And so this tends to 1 as x tends to infinity. And so I have a horizontal asymptote that is basically 1 or y equals 1. Okay. Vertical asymptotes. We're looking where the numerator is equal to 0. So where x minus 2 times x minus 5 equals 0. So that happens when x equals 2 or when x equals 5. X equals 5 is a vertical asymptote. It's definitely in that domain. X equals 2, also a vertical asymptote, just because I have an equal sign here, and I think that's right. As long as I wrote down the question correctly, that vertical asymptote is in the domain. All right, good. So that's number 11. Number 12. And so number 12, they actually, for part A, number 12 is a nice, it's a nice question with sort of a little trick in it. There we go. So it is a sequence, and it's basically 1 squared plus 2 squared plus 3 squared plus blah, blah, blah. And so the top is the sum of all the squares up to the term number. And it's being divided by an expression that is basically the term number times the term number squared plus 3. All right. And the hint here is take a look at the formula for the sum of n term numbers. So basically what you have to do is you have to go to the internet if you don't remember it, and I didn't remember it, and look up the formula for the sum of the numbers of 1 up to n squared. And so that is n over 3 times n, oh, sorry, did I say n over 3? Yeah, n plus 1. times n plus, 2n plus 1. Okay. We could put it all over 6. Yeah, okay. Let's do that. That's a little bit easier. So an easier version is n times n plus 1 times 2n plus 1. And that's all over 6. And that's being divided by n squared plus 3. Okay.
Put the 6 on the bottom. Marks this.
We can re-express this as n times n plus 1, 2n plus 1 over 6 times n squared plus 3. All right. This top actually expands out. What is the expansion of the top? This is going to be a cubic on the top.
Cancel out the n.
Cancel out the n first. Very good.
And what I got was negative.
So 2n squared
2n squared plus 3n plus 1.
plus 1 on the top, and then 6n squared plus 18 on the bottom. Okay. Now, we're going to do that same thing. What is the limit as n goes to infinity of 2n squared plus 3n plus 1 over 6n squared plus 18? And we can basically do the divide everything by n squared, which is a bit onerous. As I apply my limit in here, so these n squareds are going to cancel out. These terms are going to turn into 0, and when I throw my limit in there, it's going to be 1/3. And so that is headed for 1/3. All right, so there was a little bit of a leap in there, and that leap involved going out and finding out what the formula for the sum of the first n squared terms is. Okay, question 2. Guess I should have had these. Handier to get a hold of. There we go. Okay, so we have the first term is equal to 2. And then we have recursive definition here. So each term is found by taking the previous term, adding 8, and multiplying it by 1/2. And the question is, does this actually converge to a limit? So is there a number that this thing actually eventually turns into? And so apart from like putting in a value, figuring out what the next term is, and putting in a value and figuring out what the next term is, we can actually do this a little bit algebraically. What I will show you is how we get successive terms. And so if the first term is 2, to get the second term, we're actually going to take 1/2 of 2 plus 8. And so the second term is 5. So that's going to be really more boring than normal if I keep on doing that. The next term is going to turn into a really homely fraction, and I just don't want to do that. You would actually see this converge to a limit pretty quickly. Okay. Instead, what we're going to do is we're going to say the limit as n goes to infinity we're going to take the limit of both sides. And so this, I'm going to say, converges to a limit L. And then we're going to use our properties of limits that basically don't matter that much. The limit of 1/2 times something is 1/2 times the limit of those things. There we go. Sorry, this is being a little bit more belabored. And this is limit is equal to 1/2 times the limit as n goes to infinity of that term, in other words, the previous term, plus 8, because the 8 never changes. As n goes to infinity, the 8 doesn't change. It's always the same. Okay. If this is actually converging, then this limit is equal to that limit. In other words, the previous term and the next term really look the same as I do this. And so I can do this algebraically. So limit's equal to 1/2 L plus 4. And if I subtract a 1/2 L from both sides, I get 1/2 L equals 4. So L is equal to 8. So eventually, this expression turns into an 8. And that's the limiting value. Okay. So we have a test tomorrow. I think it's going to be pretty easy. There's a little bit of there's an outline of the kinds of questions that you might get in your test tomorrow. And it's in the course outline. Basically, the test is 5 to 7 questions, probably about 5. And they'll be marked on a level. So level 1, 2, 3, 4. And yeah, so just do your best. So they're pretty big synthetic questions. Let me see if I've got an overview here, not printed out. So determining average rate of change of a function between 2 points. Okay. Very scary. And so that's just basically using that difference quotient. So that could be, so what is the average rate of change of what's the average rate of change of f at x equals x squared between x equals -3 and x equals 3? And so you can basically say, yes, that's equal to the slope. And so that is f at -3 minus f at 3 all over -3. Oh, yeah, that's right. I've got these backwards, everybody. -3 minus 3. Sorry, the second point. +3 minus -3. In other words, f at b minus f at a over b minus a. And this works out to be 0. Anyways, that's the average rate of change. So pretty easy questions. Just use the difference quotient. Instantaneous rate of change. Which is basically the same thing as the slope of the tangent. And we had 2 ways that we did this. And so we're going from finding the slope of a secant between 2 points to finding the slope of a tangent at a precise point. And there were two versions of this where we were using the difference quotient, and we were putting in successively smaller values for h into our difference quotient. And so you would use x equals 3, and you'd use h equals 0.0001. And you would put that into your difference quotient and try and find the answer. So that's one way I might ask you to find or approximate the slope of the tangent to that curve when x is equal to 3, for example. Okay? And what is the second way? Anybody? Anybody? Algebraize it? Yes. So take the limit as h goes to 0, f at x plus h minus f at x. And so that becomes, when x is equal to 3, that is 3 plus h squared minus 3 squared all over h. And we're taking the limit as h goes to 0 of that. So it becomes 9 plus 2h plus h squared minus 9 all over h, which becomes, I didn't put my limit in. Don't put your limits in until you can actually put your limits in. And this becomes the 9 subtract out. I can factor an h out of these two over h. Now I can put my limit in, and I wind up with 2. That seems wrong. Should be 6. What did I do wrong? Oh, I see what I did wrong. Look at the expansion of here. 3 plus h squared. I put a 2h here. That should be a 6h. That's right. You fool. All right. Oh, we don't say that on the internet. There we go. 6. Okay. Does that look okay? Now that it's right? Remember we had 2 sections where we did, does the limit exist? And we talked about it graphically. In other words, does it exist from the left and does it exist from the right? And we looked at it algebraically as well. Okay, so graphically, you're going to be given one of those fancy looking piecewise functions, and it might look something like this. X, y, and this is x is equal to 2, and this is x is equal to 3. And then there's the open and closed circles. And so the question might be, identify the limit as x approaches 2, and does the limit exist? As x approaches 2, does the... No, because the limit from below is not the same as the limit from above. And so the limit as x approaches 2 does not exist. But I could ask you for the limit as x approaches 2 from above. And does the limit exist as x approaches 2 from above? It does. And it is actually equal to 3. Okay? If we talked about discontinuities, we talked about jump discontinuities. That's an example of a jump discontinuity there. Okay, we talked about extractable discontinuities. And so those are algebraic forms where we can factor the top and bottom and cancel pieces out. All right? So this would be a discontinuity. Even though the limit exists, the function is discontinuous there. You will be given a question where you're asked to find the values of a and b that make a piecewise function continuous, or the values of a and b that make a piecewise function exist at a particular point. And so it's one of those, find a and b style questions. You'll be asked to do that for sure. You'll be asked to cope with limits as h goes to 0 to polynomial functions, so fairly easy ones, and radical functions as well. Okay. Limits, evaluate the limits containing O. So when you're dealing with the radical functions, you'll need to either rationalize the numerator or the denominator to evaluate the limit. So be able to do that. And then you should be able to identify vertical asymptotes and horizontal asymptotes. You don't have to identify oblique asymptotes in functions, just like we did in the homework at the beginning. Okay. Oh, the last tricky thing. You will also need to deal with a question that looks like this. So the absolute value of x minus 3 over regular x minus 3. And so if I have a function like that, that's an absolute value function, the question might look like, explain why the limit does not exist when x is equal to 3. And so when you get a question like that, when x is equal to 3, the bottom is 0, and it looks horrifying, but it kind of cancels out with the top. But this tricky absolute value function actually makes a jump. And so if we looked at this function, the bottom and the top basically cancel out, but we have to break it up into a piecewise function. So we have to say, oh yeah, f at x is equal to x minus 3 over x minus 3 when x is greater than 3. And we have to say that it's equal to x minus 3 over negative x minus 3 when x is less than 3. And so that's turning an absolute value function into a piecewise function, just where the bottom changes sign inside the absolute value brackets. Okay? So it'll be fairly simple. Explain why the limit doesn't exist for that function. Okay, so test tomorrow. We're all good?